Hello, students. I want to think about this little example that we did just before with Sudoku because it's not just related to Sudoku. You see, let's try to draw what each of these numbers, which sets get matched with which numbers. Like 1 goes to 2, goes to 3, goes to 4, 5, 6, 7, 8, 9. Now, this dictionary here is telling us that 1 goes to 2, and that 2 goes to 1 and 3, and that 3 goes to 2 and 4, and so on. There's a name for this kind of a structure in math, where you have a bunch of things called, well, points or vertices, and each one has a collection of other points or vertices that they are connected to. And they're either connected or they are not connected. For instance, 2 is not connected to 4, but 2 is connected to 1 and 3. And this is the mathematical idea of a graph. So basically we have vertices or points, and then we have edges which connect some of the points. So what we could do here is we could say, hey, let's try to use dictionaries in order to do graph theory. So let's think of some examples. Like, for instance, one example is the complete graph. And what do I mean by a complete graph? Well, let's say we have 4 vertices, or let's start with 2 vertices. We just connect everything. So if I start with 2 vertices, I could say, hey, 1 is connected to 2. And if I have 3 vertices, I could have 1 is connected to 2. Let's try some low-budget ASCII graphics here. There. So 1 and 2 and 3 are all connected to each other. And I mean, dare I do 4? I don't really want to, but let's give it a shot. Let's do this sort of thing. And okay, that's the best we're going to do with these, with our what we have easily at our disposal. 1 is connected to 2, 3, and 4. 2 is connected to 3, 4, and 1, and so on. Everything's connected to anything. So we call this graph KN. It's the complete graph on the vertices 1 through n. Okay. So how could we store this as a dictionary? Well, one thing is if I have a particular graph, like let's say I want K4, what I could always do is I could just enter this, like 1 goes to 2, 3, 4, 2 goes to 1, 3, 4, 3 goes to 1, 2, 4, and 4 goes to 1, 2, 3. So, and you know, that gave me K4. I can see what goes to what. I don't like that so much. I think we could do this in general. So let's make a function that gives me Kn for any value of n. So what do I want it to return? Well, naively, the first thing we might think is, okay, well, I want to connect the value I to everything. So what we could do is we could say each I is going to go to the set. Well, I'm already using the set of j for j in range 1 through n plus 1. And I'm going to do this for our I in that same range. Now, this is not going to work because the way I define things, nothing has a line to itself. Like 1 doesn't have a loop to itself, 2 doesn't have a loop to itself. So if I do K4, I'm not going to get what I want. Right, because 1 still goes to 1. I don't want anything to go to itself. I'm not allowing anything, you know, with loops. So how could I fix this? Well, I could say, hey, let's try. This was a good start, right? We build up and then we somehow fix things when it goes wrong. So I basically want to take out I. And we have the set minus command for sets. So I have this set here. And what I could do is I could take that I out of it. So whatever I is, I'm not going to use it. And let's see what happens now. Perfect. 1 goes to 2, 3, 4. This is exactly what I got over here. And this works for other values as well. K3, it works nicely. K9, it's going to be big, but you can see everything is connected to everything. What if we wanted to go back to the path again? So everything in a row. So what I could do is I could define P of n, and I could say, let's return. So what we're going to do is we're going to let our vertices be I for I in range 1 through n plus 1. And now I want each thing to connect to the thing before it and the thing after it. But we already know what that problem is. So what I could do is I could intersect each of these with j for j in that same range. This way I don't accidentally leave the collection. And let's try that at P4. And as you can see, this is working nicely. Now, if you wanted to speed this up a little bit, instead of generating this set every time, what I could do is I could say, okay, I could just give this set a name, and I'll say this is the domain. And because domain is a word that we use in math for the values that we're allowing ourselves to work with. And then I can just create this domain once. You see here, what it's doing is for each I, it's creating this, I goes to this, intersect this, and it's generating a brand new list of j's for each value of I. This will save a little time. Not that you'd notice for a small value of n. I have to give it a value, but for P4. So you can see this is working just like it did when we were doing this intentionally for puzzles like Sudoku. So you're not going to notice a speed up for values like 9, and you know, by the time I get to values like, I don't know, 9 million, I don't want to actually see what the output of that is on my screen. So so we will refrain from doing that. I mean, we could always generate it by saying like D is equal to P 900 or 9,000. You could see how long it takes. So 900,000. Okay, you get a feel for how long that took. Now, if I remove this line, though, down here, so we're actually recreating that each time. Now let's see how long that takes. And we're not going to want to wait. So it is a nice speed up to only create this set once and use the same set to intersect with everything.